This video is on standard cell potential and electrode potential. Standard cell potential is the voltage that is produced by a voltaic cell under standard conditions. 100 kilopascals, 1 molar solutions, and 298 kelvins. In this case, I have a zinc and copper voltaic cell, and you can see that the voltage that is produced by this voltaic cell, which is a spontaneous redox reaction, is 1.1 volts. Electrode potential, or standard electrode potential, is the voltage or the potential difference in each of these half cells across the surface of this metal. So we would have voltage or electrode potential of the anode and the cathode. We can calculate the value of the standard cell potential by applying this formula, and that is basically the voltage across the cathode minus the voltage across the anode. The voltages across the cathode and the anode are pretty previously determined and calculated, and they're all listed in your data booklets. Here's the table of electrode potentials. These are also known as reduction potentials. You can see that the values range from negative 3.04 all the way to positive 2.87. So now the question arises, what do these values mean? And how do we determine them? And of course, how do we use these values to calculate the cell potential? Well, in my last example, I had the voltaic cell made of zinc and copper. And these are the voltages across the surface of those two metals. This is the voltage across the anode, which was zinc, and this is the voltage across the cathode, which was copper. If I were to take these numbers and plug it into this formula, you would see that this was 0.34 minus negative 0.76, and that would give me the voltage that is listed in my voltaic cell. But remember, this is under standard conditions. So what do these numbers mean? How do we get these numbers? Well, I told you to think of these as reduction potentials. You can even think of them as oxidation potentials. If the value is negative 3.04, that means that this one has a low reduction potential. That essentially means that it does not want to be reduced. So if it doesn't want to be reduced, that means it wants to undergo oxidation. So if it has low reduction potential, it will have a high oxidation potential. What that means is when we take a look at this half reaction, which by the way is written as reduction, and there's an equilibrium, I'll explain that to you guys in a bit, lithium wants to go in this direction. So you can even think of this negative 3.04 as position of equilibrium, or the spontaneity of the forward and the reverse reactions. In this case, the forward reaction is lithium plus an electron going to solid lithium, and the reverse reaction is solid lithium going the other way around. Well, based on this number, lithium wants to go the opposite way. It wants to undergo oxidation. So lithium has high oxidation potential, low reduction potential. And alternatively, on the other end here, fluorine, which we know to be a very electronegative atom, wants to pick up electrons. So fluorine has high reduction potential. That essentially means that it wants electrons badly, and it has low oxidation potential. Now that's important for you to know when you are using this table. The other thing I wanted to point out was that the values are negative up here, and then they are positive down here, and this is the value of 0. The 0 is, you will see, arbitrarily assigned to hydrogen. So the hydrogen is taken as a reference point, and then we compare the values to that. So the question is, how do we get these numbers? What do these numbers mean? Where do they originate from? What does the voltage across an electrode mean? Let's take a quick look here. So voltage or potential difference is generated when you have charge separation. So in the case of a battery, when you take a look at these two batteries here, I have a negative and a positive terminal. The negative terminal basically means that there's a larger concentration of negative charges on the side and a larger concentration of positive charges. When you have this charge separation, you have what's called potential difference in physics, and that is also known as voltage. Now, if you compare the two batteries that I've shown you here, this one has fewer charges, so 2 negative and 2 positive in this case. And you can see that this is giving you a higher potential difference, this is giving you a lower potential difference. That essentially translates to a higher voltage battery and a lower voltage battery. So if you have charge separation, you have potential difference, and you have voltage. Now, of course, we can measure that voltage of a battery by using a multimeter or a voltmeter. So how does this concept apply to electrodes that are placed in solutions? So again, we are trying to determine what these values mean, and of course, we're going to take a look at how they are actually determined. All right, when we take a look at an isolated electrode, so in this case, let's say I'm looking at zinc and I place it in zinc sulfate, but I'm not making a voltaic cell. This is completely isolated. Even though it's isolated, what will happen here is zinc will undergo oxidation. So zinc will produce zinc 2 plus ions plus 2 electrons. What happens is that the zinc 2 plus ions go into the solution, and then these 2 electrons will basically sit on the surface of the zinc metal. Now, this will happen until you reach what's called redox equilibrium. So the forward reaction will go, so zinc will produce zinc 2 plus ion plus electrons, but at some point what will happen is the zinc 2 plus ions will start to come back and pick up electrons from the metal, and you will have a reverse reaction that happens. And that's the reason why we have an equilibrium arrow in that table. Now, once this happens, then we have a net positive charge inside the solution because of the zinc 2 plus ions, and we have a net negative charge on the surface of the metal. And because we have a charge separation, now we have a voltage or a potential difference across the surface of this electrode. And that's essentially what those numbers measure. You can see here with copper as well that something similar happens. The only difference here is that you notice that copper does not produce as many electrons. So copper does not undergo oxidation as quickly as zinc. So you can see the charge separation in copper is not as much as this. So this will typically end up with a lower voltage. That's basically equivalent to what I was telling you here. So if you have large charge separation, this is going to be a higher voltage. And if you have smaller charge separation or fewer charges, then this will translate to a lower voltage. So the question now is, how do we determine these numbers? Well, let's take a look at how we determine the voltage of a battery. This slide is just showing you that if you were to connect zinc to copper, because zinc has a higher charge separation, there's more electrons. Electrons will automatically flow from zinc to copper. So just keep that in the back of your heads. How do we measure electrode potentials? Well, this is how we measure the voltage across a battery. You will take a multimeter, you will connect it to the positive and the negative terminals, and you get your voltage. Unfortunately, I can't use this machine to measure voltage across an electrode in solution. So we use what's called the standard hydrogen electrode. Now, the standard hydrogen electrode, the acronym is SHE, is an electrode that basically contains hydrogen that is dipped in a solution of a strong monoprotic acid, and the concentration of the solution is 1 molar. Strong monoprotic acid would be HCl, HNO3. Monoprotic meaning that they have a single proton, and there is also a platinum electrode. So typically you'll be asked, what are the 3 components of this standard hydrogen electrode? Well, it's hydrogen gas, there is a strong monoprotic acid as an electrolyte, and you have a platinum electrode. How do we use this to determine the value of the electrode potentials? Well, we connect it in a voltaic cell to the metal of interest. In this case, I'm trying to find the electrode potential across zinc. We know that there is a negative charge built up here, and we know that the solution is positive because we just saw that earlier. As soon as you connect this, what will happen here is electrons, in this case, flow from zinc to standard hydrogen electrode. That cell potential that is listed here is taken as the electrode potential of zinc, and this guy is assigned a value of 0 arbitrarily. So why is 0.7, why is the value of zinc, when you take a look at this table here, why is the value of zinc negative? And you notice that zinc is placed above hydrogen. Well, if electrons, when you build this voltaic cell with standard hydrogen electrode, if electrons flow from the metal to the standard hydrogen electrode, the voltage this one here is placed higher on the table, and the value is taken to be a negative number. If alternatively electrons flow from standard hydrogen electrode to the metal here, this value is obviously taken as the electrode potential of that metal here. If electrons flow the other way, then the copper or in this case copper, or that particular metal, whatever it is that we're looking at, will be placed below hydrogen and it will have a positive value. So just to quickly summarize here then, when we are looking at standard cell potential is the voltage that is produced by the voltaic cell, and it can be calculated by taking the voltages of the electrodes and taking the voltage of the cathode minus the voltage of the anode. It's important for you to understand what these negative and the positive value now tell you. Now, if I'm comparing something that has a negative value of 3.04, that means that this particular element wants to undergo oxidation. This table is typically used for identifying anodes and cathodes. So for example, if I wanted to build a voltaic cell with lithium and zinc, you can see here zinc in my last example was the anode, but in this particular case, if I was building a voltaic cell from lithium and zinc, in this case, because lithium has a higher oxidation potential or lower reduction potential, lithium would be my anode, and the zinc here would be my cathode. Okay? Now, because lithium has a low reduction potential, high oxidation potential, lithium is a very strong reducing agent. You guys will recall from our introductory studies on redox that reducing agents are the ones that are producing electrons, and they cause other elements to be reduced. Now, the last thing I want to mention here is when you take a look at the left side of these half reactions, you can look at the oxidized species here. So when I take a look at lithium plus will pick up an electron to form lithium. Now that process does not happen readily because we know lithium wants to undergo oxidation. So, which means that lithium plus will not want to pick up an electron. Now, lithium plus is going to be an oxidizing agent. In fact, all of these ones on the left side here, by picking up electrons, they will be causing the oxidation of their reduced species. So lithium plus is a weak oxidizing agent. So zinc 2 plus would be a stronger oxidizing agent than lithium. A quick summary then here is that in terms of reducing and oxidizing agents, the strength of the reducing agents increases from top to bottom. So as you go from top to bottom here, you go from weak reducing agents to strong reducing agents. And as you go on the left side from top to bottom here, so when you go down, the strength of oxidizing agents here increases. So lithium would be a very weak oxidizing agent, whereas fluorine would be a very strong oxidizing agent.